Welcome back, and off we go. I want you to remember the two reactions that we like to talk about, the main one being the Ka reaction for an acid. And here's a generic acid, H bonded to anything. How's that? And I want to talk about the Kb reaction for the conjugate base, which is A minus for A minus. Nope. If an acid reacts with water, then it's the Ka reaction. If a base reacts with water, then it's the Kb reaction. They both are related to water. And here's the base. And what's an acid going to do to water? Well, acids are proton donors. Water will be accepting the proton, so water's acting like a base. It will take on an extra proton, so water will become H3O plus. Hydronium. HA will be converted to its conjugate base. Let's make sure we know these are clearly two separate discussions. A minus is going to be a base in the next one. Okay, thinks they're linked. It's fine. How about this? I'm wasting my time. Here we go. A minus will take an H plus from water. What's H plus also called? Proton. Water becomes hydroxide. A minus took a proton, became HA, back to its conjugate acid. Ka is the hydronium concentration. Remember, products concentrations over reactants concentrations, leaving out things like solvents, and if you remember from 141, solids as well. We won't deal with solids here. How's that? Make your life easier. Two products there, only one reactant because water is also the solvent and its concentration will not change. Kb over here, hydroxide times Ha. All over A minus. So for a conjugate pair, if you multiply Ka times Kb, I took everything from here. Oh, I see this is really, they're backwards here. That's fine. I did Kb times Ka when I said I was doing Ka times Kb. Please don't be confused. Please don't do any of this because all you have to do is believe the box. Okay. All right. So Ka times Kb, Ka times Kb, a lot of crossing off. And you're left with hydroxide times hydronium, which the other day we learned the product in any aqueous solution of hydroxide times hydronium is always this value, 10 to the negative 14. So Ka times Kb is 10 to the negative 14. Take the negative log of both sides. The negative log of Ka is called pKa. The negative log of Kb is called pKb. The negative log of 10 to the negative 14 is negative 14, also known as 14. There's the thing we used on our previous question. All you have to do is believe it's true because it is and just use it. So if you want a pKb, you take 14 minus pKa. So we got that covered now. And then coming up here, We have a very bold statement that I really don't think you should share with your biology teachers until you've had a little more experience. But imagine walking up to Miss Brand or Dr. Garrett and saying such a thing as this. Oh, there's no such thing as an amino acid. Okay, just let that sink in for 2 seconds and then I'll try to explain what I mean. Here I started with a carboxylic acid and a normal amine, and I did all my stuff. I did acid-base reaction. This lost a proton. It became a acetate ion. You remember that ion, don't you? This gained a proton and became an ammonium ion. Yeah, ammonium ions don't have to be NH4 plus. They can have carbon groups as well with a pKa of 10. Do the pKeq analysis and then the KEQ, and it's 100,000, which means this arrow should be 100,000 times bigger than the backwards arrow, and that would be just a dot if I did 100,000 times smaller. So bottom arrow's too big here. The fact is, at equilibrium, when you're done, the product of these two multiplied by each other is 100,000 over one of these. Wow. You have 100,000 times more products than reactants. You have 100,000 times more ammonium ions and carboxylates than you have amines and acids. Does this argument change if they happen to be connected in the same molecule? No, that'd be an octet violation. That's okay. I fixed it. It doesn't change a thing. The same rules apply. pKa rules cannot be disobeyed. So that's what the bottom example has. They are connected already in a molecule called an amino acid. Here is what it would look like if it was an amino acid. It would look like this with an amino group and a carboxylic acid group. This species does not exist in reality. That's what the whole topic at the top of the screen is. This species, there's only one of these molecules for 100,000 of these. It's as if you have, let's see, we got Michigan Stadium holds over 100,000 people. So we've got the big house. You got 100,000 people there. Let's make this outlandish. You got 100,001 people there. 100,000 of them are gentlemen and only one is a lady. And if you're trying to tell me that stadium's full of women, you're flat out wrong. I wouldn't even see the one woman in there. There's 100,000 men right here and one woman. I am exaggerating the split of men and women during football. Please don't read into that. The truth is, there's zero of these for 100,000 of these. 1 over 100,000 is like 0, isn't it? So we don't say there's an amino acid present. We say there's an ammonium carboxylate present. And that species in this form is the realistic picture of what an amino acid really looks like. And it's called the Zwitterion form. Yeah, I said with the German pronunciation there, Zwitterion. It derived from the German words zwei and ions. I like the German language for that reason. They like gluing words together. They're called portmanteaus. One of my favorite portmanteaus in English is Velcro. A lot of people don't know that. It comes from velour, a soft fabric, and crochet. Isn't that exactly what Velcro is? Okay, sorry, total aside. Zwitterion is another portmanteau that says what it is, 2 ions. And there you go. That's what an amino acid really looks like. Bold statement. Better back it up with numbers. Okay, now we're going to look at the Henderson-Hasselbalch equation. And as soon as we start talking about that, you should start thinking about buffers and looking at this saying, oh, is he going to make me use this on a test without a calculator? Then I'm cooked. And I would agree with you. I will not make you use that equation on a test. And I will not let you use a calculator, but we're going to conceptualize that equation. And you'll see how I do that in the last segment of today's class. And for now, what's happening here is an acid is reacting with water. This is the Ka reaction to make hydronium A-. There's Ka. You don't have to do any math for me in this class about reorganizing algebraic equations. I'm doing it for you here. Just tell me if I did something wrong, and I didn't. I've checked. I divided both sides by A- and multiplied both sides by HA, and I came up with this. And then I took the negative log of both sides, and I got this. The negative log of hydronium is called pH. The negative log of Ka is called pKa. The negative log of HA over A- is the same as the positive log of A- over HA. That's just math, people. Here's the equation. Am I going to make you memorize it? No. Am I going to make you remember two very simple facts about acids and bases that you probably already know? Yes. What do acids do to pH? Do they lower the pH or do they raise it? The answer is acids lower the pH. Hey, if you got a big number down here and a small number up here, you're going to get a fraction. The log of a fraction is a negative number. You're going to add negative to this. The pH will be below the pKa. Now, what do bases do? Remember, A- is the conjugate base. What do bases do to pH? Forget about the equation. Bases cause the pH to go up. So if I have a big number here, it means there's a lot of base, and a small number here, which means there's not a lot of acids. So say out of 10 to 1 here. What's the log of 10 to 1? That's 1, positive 1. Your pH is going to go up. It's even easier to memorize than that. Bases raise pH, put them up. Here, it's up. Acids lower pH, put them down. Down. There, you got it memorized. So when you have a mixture of a weak acid and a conjugate base, which is always also weak, I'm going to write that down. That seems important. When you have a mixture, am I typing okay? Yeah. Mixture of a weak acid and its conjugate base, which is also weak. The Henderson-Hassel, that's tricky spelling, Balch equation governs the pH of the, here's the magic word, buffer. Buffers are very important, especially in biochemistry. That has to be red. It has to be big. Yes. It's not red. It is now. Mixture of a weak acid and its conjugate base, which is also weak. All right. So the question is, do we have a buffer if I have a mixture of an acid and a base? And the answer is not always yes. It's very specific. It has to be weak acid, weak base for very good reasons. So buffer, not buffer. That's a question for now. Buffer or not buffer. And the definition of buffer is hidden in there. When you have a mixture of a weak acid and its conjugate base, it's a buffer. It's in there. The middle part says, oh, If you got a buffer, you can predict the pH using this equation. There you go. And that's a question mark. So I'll start off with our favorite acid and its conjugate base. Everybody thinks of HCl when they think of acids. And what's the conjugate base of HCl? Conjugate base has one less proton. Take away proton from HCl. Proton is H+. What do you have left over when you take H+ away from HCl, which was neutral? Cl-. And that's a not buffer. I know I've got the definition in words up here, but I like the definition in concept. Buffers work by being able to neutralize external acids or external bases. That means if I add an acid to a buffered solution, that acid will be neutralized. What will it be neutralized by? The base in your buffer. If I add a base to my buffer, it will be neutralized by what? It will be neutralized by the acid in the buffer. If one of those two species is strong, like HCl, means this thing can neutralize any base you add to it. No problem. But because HCl is strong, chloride minus is no kind of base for a buffer at all. It's too weak. Okay, so no. And the answer, I mean, it's not even going to use the definition. Cl minus is too weak. Too weak to neutralize any acid. So that's not a buffer. Let's do another extreme. What's your favorite strong base? Sodium hydroxide? Sure. I didn't even hear you say sodium. Hydroxide. Why did I say I didn't even hear you say sodium? I said sodium. That's a spectator. I crossed it off in my mind. What is the conjugate acid of hydroxide? Well, add H+ to hydroxide because the conjugate acid has an extra proton. And you get H2O. And it's not a buffer. Why? It has nothing to do with the fact that hydroxide's a great base for neutralizing acids. Water is a terrible acid to neutralize any base. H2O is too weak. Too weak here of a base of an acid to neutralize any base. So this is why they're not good buffers. It doesn't really use the definition of buffer, but it's hidden in the definition. This is strong, and the buffer needs to be a mixture of a weak acid and a conjugate base, which is weak. Also weak. Base is weak in that case. Well, because this is strong, this is too weak. Similarly, because this base is too strong, the acid's too weak. You're saying, when the heck can we ever have a good buffer? Well, here's a very common buffer, a mixture of acetic acid and its conjugate base. Came up earlier, we called it acetate. What's the pKa of acetic acid? It's 5, which means it's weak. What's the pKb of the conjugate base? Oh, it's also positive, which means it's weak. Going back here, pKa -5. Here, don't put a pKa under hydroxide. It's not the acid. Here, the pKb equals 14 minus -5. Oh, this is terribly weak. Okay. Strong will always give terribly weak. Similarly here, weak comes from terribly strong. pKb, 14 minus 16. Too strong, which means this is too weak. And there you have that. So on our last segment today, we're going to continue with more discussion of buffers and how we can avoid using calculators and get the right answer on our test. Because doing logs without a calculator is a nightmare. There's one teacher that can do it in chemistry. His name's Dr. Yackel. And here we go.